Hello everyone, I am Minendra Surve. We are in the lecture series of Vibration Control, University of Mumbai, semester 7, and we are going to discuss a very good numerical on the base of whirling of shafts or critical speeds in the shafts. Before going to discuss that numerical, I would like to ask you, we will go through this theory concept, and once you understood the theory concept behind it, you can easily solve that numerical. I welcome all of you in my YouTube channel, and let's start with our new topic of vibration control, that is whirling of rotating shaft. Now, what do you mean by whirling? What do you mean by critical speed, or what do you mean by VP? So, a rotor system, any rotor system, that is rotor or a shaft, that we are assuming that both the rotor system or shaft are in a rigid positions. But in practical applications like turbines, pumps, compressor or electric motors, the heavy rotors, that heavy rotors are mounted on a flexible shaft or lightweight shaft, and that shaft is going to be bent due to some kind of we can say manufacturing errors or unbalance. Due to that unbalance, our shaft is going to be bent. Okay, in case of turbines, pumps, compressors, heavy motors, our motor is our this rotor or disc is a very heavy. Due to that heaviness, some unbalance is associated with the disc, and due to that unbalanced force, or due to some kind of manufacturing errors, due to these kind of causes, that at that speed, at what speed our shaft is going to bend, at particular speed our shaft is going to bend, that speed is nothing but your whirling or whipping or critical speeds. And why this unbalance is occurs? Due to some kind of manufacturing errors or some kind of damping errors, or maybe heavy rotational RPMs, or a lot of many practical errors, or a lot of many practical issues are with. And you need to remember our shaft is going to be bent at particular speed, that speed is your whirling speed. Okay, and again due to that whirling movement we have got a steady state amplitude. Again, that is very important thing. Practical wise, they will never ask you the derivation on this, but you have to remember the end results, because if you want to solve any kind of numerical, I always said you that you need to remember the end results, not a whole derivation. So the steady state amplitude, due to this whirling effect, due to this whipping effect, or due to this critical speed, we get steady state as ar square divided by under root 1 minus r square bracket square plus 2 zeta r bracket square, where our zeta is a damping ratio, zeta is our damping ratio, and we can say here our r is the frequency ratio, frequency ratio, that is already known to us. And what about this a? This a is nothing but eccentricity. Eccentricity means both the center of the shaft as well as center of the rotor, how much they are going to offset. That offset distance or that eccentricity value is given to you in the question paper or in the numerical, and with the help of that data they are asking you to find out what will be the steady state amplitude, or what will be the steady state amplitude during initial phases. So this kind of question they are going to prepare. So we will see the numerical. So I have here with a very good question of from critical speed of shaft or whirling speed of shaft, and the question is mentioned over here. So this kind of question you can expect in the upcoming university examination of Mumbai University for 7th sem for vibration control. And this question is again very good question taken from the reference book, or you can check here a shaft carrying a rotor. So we will go through a question, a shaft carrying a rotor. So shaft is given, and inside that shaft we have mounted a rotor, mass of 40 kg and eccentricity is 2 mm. So eccentricity value that I am going to discuss in the previous theory section, that eccentricity value is provided and eccentricity offset distance is given as a 2 mm. Rotates at 1200 rpm. So rotational speed of the rotor or disc is given as 1200 rpm. That they are asking steady state whirl amplitude. Okay, whatever you have formula in results have mentioned earlier, that is again asking what is your steady state amplitude or whirling amplitude. Okay, that is nothing but they are asking capital A value. Okay, now again the maximum whirl amplitude during startup conditions. So again it is a critical question. Maximum whirl amplitude they needed, but during a startup condition we will look out what is the meaning of that section B. Okay, and for that assume stiffness of the shaft is 350 kilonewton per meter. The stiffness of shaft value is provided 350 kilonewton per meter, and external damping ratio as 0.1. So that is nothing but external damping ratio zeta. Critical damping ratio we usually call as damping factor. So that damping factor or damping ratio is given as a value of zeta. So how we are going to solve it? We will proceed. Whatever is the given data of mass 40 kg, eccentricity 2, and rotates at 1200 rpm. So first what we will found out, forcing frequency of rotor. So here we can easily found out the forcing frequency of rotor, because rotational speed is given in terms of rpm, that is 1200 rpm. So the forcing frequency of rotor we can easily calculate, that is 2 pi into n is equal to 1200 divided by 60. This value is given. So omega, what we will get value of omega is 125.66 radians per second. This value we can found out. Then again we can find here natural frequency. So natural frequency we can easily calculate for system. Natural frequency you can found out from here. The natural frequency of the system. Whenever the given data is to you observe it, and from that given data whatever we can conclude, whatever we can found out, and then solve what they are asking in the question. So utilize the given data first. So we can easily find out natural frequency of the system. So lot of vibrations questions are solved with the help of this given data. So natural frequency we can easily calculate, because natural frequency is known to you. Omega n is equal to under root k by l, and value of K stiffness is provided. And how much is the value of stiffness? 350 kilonewton per meter. So we will take 350 into 10 to the power 3 newton per meter. So put the value omega n is equal to under root, how much it is? 350 into 10 to the power 3 divided by m. Mass of the rotor is given as, how much is the mass of the rotor given? Mass of the rotor is 40 kg, I guess. Yes, it is 40 kg. So what answer you will get here? You will get answer omega n after solving this 93.5414 radian per second. So you will found natural frequency is 93.5414 radian per second, and this is omega. It is angular speed. Okay, now from this data again what we will find here, the frequency ratio, because frequency ratio is what? R is equal to, frequency ratio R is equal to omega by omega n. That is aware about, we are aware about this. So this is 125.66 divided by omega n, that is 93.5414. So frequency ratio here we obtain is equal to 1.3433. This is the frequency ratio. Now what they are asking what is a steady state amplitude. They are asking steady state amplitude. Steady state amplitude, how we have found out steady state amplitude? In a theory session I have mentioned steady state amplitude. A part they are asking steady state amplitude is equal to AR square divided by under root 1 minus R square bracket square plus 2 zeta R bracket square. This is a formula. Steady state amplitude AR square divided by under root 1 minus R square bracket square plus 2 zeta R bracket square. And the value of eccentricity. Value of eccentricity is given. A is equal to eccentricity. How much it is given? Eccentricity is given as 2 mm. So you need to take that is in meters. 2 into 10 to the power minus 3 meter. Again, damping ratio zeta is given as 0.1. Okay. So just simply put the value and found out. We are putting the value over here. Look at here. We are just simply putting A is equal to A value 2 into 10 raised to minus 3 R square. This is value of R 1.3433. We are taking a 4 digit 1.3433. Square of that divided by under root over is 1 minus 1.3433 square of that again whole square plus 2 zeta value is 0.1 into R square, that is 1.3433 square 2 zeta whole square. So after solving this, you will get value of steady state whirling amplitude, that is nothing but near about 4.2552 in mm. So that much of the amplitude you will found out. Whirling amplitude or steady state amplitude during 1200 RPM. The RPM is given, that particularly RPM you will get critical whirling speed. At that you will found out steady state amplitude. What will be the steady state amplitude? That is 4.2522. Again the next question is a B part. That is very important, B part. What is B part? They are asking. During the startup conditions, the frequency speed during startup condition. They are asking during startup. During startup conditions, the frequency speed. Yes. What will be the amplitude during startup conditions? The maximum whirling amplitude during startup condition of the system. They are asking. So during startup condition, your frequency of a system omega is going to match with the natural frequency of a system. Only you need to be remember over here. Your frequency, what? The rotor, angular speed of a rotor is going to match with the natural frequency of a system. Angular speed of a rotor omega is going to be matched with angular frequency of a system. This is nothing but if our omega and omega n are same, then frequency ratio is equal to omega by omega n is equal to 1. During startup conditions, what will be the steady state amplitude they are asking? But during startup condition, the angular speed of a rotor that is going to match with natural frequency of system. Okay, I have shown the figure. The rotor is mounted on that shaft. Okay, so your natural frequency of rotor is going to match with natural frequency of system is going to match with rotational speed of rotor. Okay, so here your R frequency ratio is equal to 1, and again if our frequency ratio is 1, then if you look out here, if frequency ratio, if you put R value is equal to 1, what we will get here? Directly that is going to be reduced. If 1 minus 1, this is going to 0, and only the term is remaining. Frequency ratio is 1 means here you will get, we will write here A is equal to A R square, or R is equal to 1, frequency ratio is 1 means in the numerator you will get A, and then in denominator this term is going to 0. If your R value is equal to 1, this term is going to 0, and here R is equal to 1, square and square root will get cancelled. A divided by 2 zeta is the remaining. A divided by 2 zeta. And what is our A value? You can put here value. What is your A value? A is nothing but eccentricity, that is 2 into 10 to the power minus 3 divided by 2 into zeta, that is 0.1, and you will get, after this solving, you will get 0.01 meter. That is nothing but steady state amplitude during startup condition is near about 10 mm, and that is your answer, final answer. This is final answer. Again, this is final answer for case A, and this will be a final answer for case B. Case B is a crucial. Only remember, during initial phase or startup condition, your frequency of a system is going to match with angular speed of rotor or a disc. That is the case, and that's why we are taking frequency ratio is 1. And after solving, frequency ratio is equal to 1 over here. This term is vanishes. This term is going to get 2 zeta in the denominator, and numerator you will get A only. And steady state is reduces to a 10 mm. 10 mm. Yes, right. Before that, we have found out A is equal to 4.2525. Okay. If you have any kind of doubt in this solving approach or in this theoretical session, you can comment me in the comment box. Or if you are having any kind of a question that is unsolved, text me that unsolved question. I will try to solve that question. And if you like this content, please share it with your friends, and please subscribe us. That is one of the important thing. And welcome all, and all the best for your final exam. Thank you very much.